Welcome back to biology. Today we're talking about why water is weird, and by weird I mean awesome and amazing and necessary for life. So let's get into it. Remember, we have the second big idea for the unit, this second half of Unit 2A, and that's to explain the importance of water to cells, water and carbon. So we're going to use two learning targets to do that. They're pretty general today. We're going to talk about specifically how living things like plants use water and get it into their system to grow, reproduce, and maintain their structure. And we're going to describe the importance of water to living things. That's pretty generic. Just make sure that you understand why water is important and why it acts the way that it does. So I'm going to start by showing you one demo, and I want you to just observe what's happening. I'm going to speed it up a little bit and be observant and see what's going on with the situation. So I'm pausing the demo here just to point out that what you're supposed to be looking at and observing is, notice the level of the water in the glass. Now that was a full glass before this person started putting all of the paper clips in there. So we're wanting to see what you'll predict will happen. Okay, they're all in, and they're going to show you a close-up here in just a second. Okay, so the video music was pretty dramatic. But at the end, you should have seen the water was sort of bubbling over the top, but holding itself. So the question is, that I want you to think about for class, is why do you think the water took so long to spill over? I don't think that you actually see it spill over in this video. It held its form for quite a long time. So think about that for when we get into class today. I have another demo for you, so let me get that set up for you guys.
This is a simple science trick that you can perform. All you need is some pepper and a little dishwashing detergent. Pour some water into a shallow dish. Shake some pepper on top of the water. If you put your finger into the dish, nothing much will happen. To perform the trick, all you have to do is dip your finger into a little dishwashing detergent. Now when you go with the water and the pepper, something completely different happens.
Okay, so I want you to think about what's happening on the surface of the water now that we've added a little detergent. We're going to talk about that in class today. All right, so there are several characteristics of water that result because of the hydrogen bonding that we talked about the other day, yesterday, and because the fact that water is a three-dimensionally bent polar structure. Because of those things that we discussed yesterday in terms of its structure, we're going to talk about how that functions and why that's weird for molecules that are of a similar mass and size. All right, the first one we're going to look at is its phase of matter. Water is a liquid at room temperature. It's actually a liquid at quite a large range of temperatures. And it has a very high point at which it boils and a high point at which it freezes comparative to other molecules of a similar size. So if we compare that to methane, which has only 5 small atoms, and oxygen, which has 2 small atoms, all of which are covalently bonded, if you look at their molecular mass, if you could measure the mass of those molecules on the atomic size, then water is actually somewhere between those two in terms of how much mass it has. So it's quite comparable to these two. Look at the state of matter that methane and oxygen are both in at room temperature. Okay, so both of those are a gas. Oxygen is the gas all around you that you breathe in, and methane, you don't want to breathe that in. That's a fossil fuel byproduct. But look at the boiling point. Now, granted, this is Celsius, but you know that water boils at 100 degrees Celsius. Well, if you look at that in comparison to methane and oxygen, these values are negative. So that means these have boiled off of a liquid state and into a gas at negative 161 and negative 183. And this is positive 100. So it's a huge difference. And that's because methane and oxygen, they don't have the hydrogen bonding that water has. And they're not polar, so they don't have that polar attraction as well. There's no hydrogen bonding between the hydrogen of one methane and the carbon of the other. It's only H to NO or F. And there's no hydrogens in oxygen, so they're not present in there. Also, the melting point. You know that solid water, ice, melts at 0 degrees Celsius, but methane and oxygen, you'll never see those as solids because they are so cold, right? Celsius. You'll never see those as solids. So we talk about that in terms of its high specific heat. Because of the attractive forces that hold those molecules of water next to each other more than, say, other molecules of a similar mass and size, it takes a long time, a lot of heat energy to heat it up to force it to a phase change, like evaporation. It also holds that water, or that heat, I should say, for a long time. Now, I have a pool, so I know that if I jump in the pool in the morning, it's cold. That's because I haven't had any heat being applied. It's taken all night to cool down. If I jump in the pool in the morning, it's cold. If I jump in the pool in the evening, it's warmer in the hot summer because the sun has been beating down on it all day and it's retained that heat for most of the day. Okay, but if you were looking at any other similar molecule, it would have lost the heat and evaporated away much faster. So that's property that you need to know about. It's called a high specific heat, but that's what happens. Okay. It is a solid that floats in a liquid. Now just take all of the concepts you have of ice away for a minute. If you put a solid rock in water, would it float? No. Right? There are very few solids that are less dense enough to float, okay? Especially for their own substance. Most of the time when you have a solid, look at this up here. The particles in a solid are much closer together. They're more attracted to each other because they're moving slower. In a liquid, they are more fluid, right? They're less rigid in structure, okay? And so oftentimes for a substance, its solid phase will be heavier, i.e. denser than its liquid phase. So if you put a chunk of it on top of a liquid, it would sink. But that doesn't happen with water. Float ice cubes in a glass, you've learned that already. So let's look at the structure of water in its three-dimensional, I should say molecular states, in its three phases of matter. So cold water moves very slowly, but they're still not stopped. They haven't stopped moving. They're still sliding past each other. Warm water, they're moving much faster. You should be able to see that there's more space between these particular molecules than these ones, and that's because they have more kinetic energy to move around. They're warmer. But at some point, the warm water, as it cools, because they're going so slow, those forces like hydrogen bonds and polarity force the water molecules to line up kind of like a lattice. We call it a lattice or a fence. Have you ever seen, you've seen a chicken, like a backyard fence? And the way that they arrange themselves with these hydrogen bonds between the hydrogen of one and the oxygen of the neighboring molecule create a space. Now, I'm not going to say that that is air. That's not air. On a molecular level, this is just empty space, because you would see air molecules if there were air in there, and there's not. These are tiny, tiny, tiny atoms. So there is space between them when they're frozen to a solid. That is very unusual. Most of the time, solids are closer, their atoms are closer together than they are in a liquid. So that's another way that water is weird, because these intermolecular forces, the hydrogen bonding and the polarity, force them into a rigid structure with space between the molecules. Space means lighter, less dense. All right, cohesion. Co means together, and here, or adhes, like tape, right? So cohesion is to stick together, and that's the tendency of water molecules to stick to each other, right? So in this case, you can see that they have a very high attraction, affinity for each other. So this little illustration here shows you what molecules that are undergoing cohesion would look like in a vacuum, okay, in a space. And this is what they would look like without. They would move to fill the shape of the container. Okay, so water molecules have cohesion between them. That makes them stay together as molecules. Cohesion results in surface tension, because if you could look at all of the molecules in this droplet of water, if you look in the center at the arrows between the molecules in the center, those molecules have attractive forces all around them. They're all attracted to the one next to it. But at the surface, where there's no water, just air, those molecules are not attracted to the air. Instead, their attractive force is downward or inward into the droplet. So imagine them all holding hands, and the ones on the end are like holding to the ones inside of the droplet. Okay, and that ends up with what we call a high surface tension. The surface of the water is almost like a thin film that certain, for example, water striders here can actually walk upon. You may have seen that video, and I'll probably find it for you. That lizard that runs really fast, it's called the Jesus lizard, but it runs so fast it runs across the water, right? And that's because it's moving so fast, its mass is not really touching the water. And it also results in the ripple nature of water on the surface. So cohesion makes surface tension. Here's another, a better picture. I'm sorry that this keeps showing up. There you go. So this is another picture. I just zoomed it in for you. Cohesion is stronger between the molecules in the middle. All right. So what ends up happening is this skin around the outside. Adhesion is similar, except instead of together, adhesion is where they adhere to other molecules. In this case, in biology, we usually look at it in terms of plant molecules, right? So adhesion is where they're attracted to other things. Okay, so that's when, like, molecules might have an electrical charge, or they might be big enough that the water just sort of is attracted by the same sort of forces that pull big things into planets. Okay, so that's why water stays on your car until it evaporates, because it's attracted to the metal in the paint, okay, on the surface of the car. So cohesion, adhesion. Together, those two are really important because they result in something called capillary action. So a capillary is a long tube like a straw. We use these kinds of tubes for IVs in the hospital when you have to, like, get saline or some kind of fluid into your veins. They'll put a needle in your vein, but the tube is like an extension of your vein. So that's how they can get the liquid to travel from the bag into your into your own internal capillaries because the adhesion of the water molecules close to the edge of the tube are sticking to the tube, but they're also pulling along the water molecules behind it. And so what that ends up looking like is a meniscus that is concave. So there's a dip in the middle. Next time you're drinking out of a straw, look at it. You'll see that there's a little dip in your straw, and the water in the straw is higher than the surface, or I should say the liquid in the straw, but it's probably going to be water-based, is higher than the surface of the liquid in the glass. That's different than other liquids, like, for example, mercury, which is Hg. Mercury has a convex meniscus. The surface of it is not attracted to the walls of the tube that it's in. So there's no capillary action. There's no pull of the mercury molecules up that tube. Here's another look at it. We apply this when we talk about plants as well, because plants have pores in them. In fact, hold on. Hi again. Sorry, I took a little minute because I remembered that my son was playing with a big house tree plant that we have, and I asked him to save me some to show you. So if you look closely at the stem of this, he's peeled it for us, thank you. But if you look closely at the stem of this, you should be able to see tubes like teeny tiny straws that the water flows through. And if you turn to the side, I had him cut it so it's easier to see. If you turn to the side, you can see how the water would travel through these little cavities, and gravity would hold it in the cavity, but as the water travels from the root to the leaf and the water gets evaporated, it pulls it along, just like in a straw. So thank you, Lachlan, for contributing to my science teaching. I really think this is a cute analogy, but it will help you remember adhesion to the side, cohesion together. So the ones on the side of the tube are pulling up the other ones. So in a plant, oopsie, where are we at? Yeah, in a plant, if you look at that closely, again, so here are those little, I don't know how well you can see that. Here are those little veins and tubules we talked about. They're called xylem and phloem. We'll talk about that next semester. But if you can tell from the picture here, you can see the little red dots are the hydrogen bonds. So the molecules of water on the edges are hydrogen bond attracted. They're attracted to the side of the xylem of the plant. And then the hydrogen bonds between the molecules would be the cohesion, and that's pulling up everybody else in line. So what I've provided for you here, and I'm going to give this to you with live links. I'll put it as a link in your content. But this is some simulations and animations that I found to sort of reinforce these separate concepts we've talked about. I talked about universal solvent yesterday. So if you want to play with this animation, I'll let you do that. You have to download it, but it's safe. You can download it from this site. Okay, well anyway, these are just ways for you to visualize and play with it on your own. I'll give that to you as live links. Okay, and then in class, I'm going to be asking you about this stuff today. Thanks, guys. Remember that if you have any questions, reach out to me.